Hello, I'm Jared Salvo. I'm here to present my project for Computer Science 7300 in unsupervised learning. My project is to perform PCA, principal component analysis, in a functional way. So what I wanted to do was to use Clojure, which is a programming language on the JVM, and a highly efficient matrix library called Neanderthal to implement an unsupervised approach, namely PCA. So in this project, we have this kind of book along with the corresponding scripts which you can find at the bottom. If you click it, you go to the script itself and then the project itself. So within this project, you can replicate it on your own machine because there is this thing called a dev container. And how to use your dev container, you can see near the bottom, down in this section, you would need Docker, or VS Code, or a fork, and the extension dev containers. And you'd be able to set up your own project exactly as this. So in this project, we have multiple scripts, multiple chapters in this book. Descriptive statistics, I'm not going to talk much about, but the point here I want to emphasize is the Neanderthal library. So this library, again, is an efficient and fast optimized matrix operator library. So just as an example, an arithmetic mean were used to this equation. So take the sum of all your values and divide it by the number of values there are. Now look at the mean implemented using Neanderthal. Again, they have these functions called sum. They have a function called dim. And instead of looping through all of the vector itself, it takes one snap and takes the sum of that vector and the dimension of that vector, which effectively is the n, and it divides them. So you have your mean. This is descriptive stats. Take a look. There's a lot of code here that's used in other chapters or scripts. So here, eigenvalues and eigenvectors. This is our master equation. A square matrix A times this phi, which is an eigenvector, is equivalent to a lambda, an eigenvalue, times the same corresponding eigenvector. This is a master equation, and we can compute some of these values, this eigenvalue, eigenvector pair, in different methods. So one method is called this power iteration method, and effectively, and incidentally, by the way, you see x's sometimes for eigenvectors. You'll see a v sometimes, which this is a typo because here I have 5s, but you'll see v sometimes, you'll see x sometimes, and you'll see phi sometimes. So sometimes you'll see av equals lambda v, ax equals lambda x, and so on. It's a little confusing, but stay with me, we'll get through it. So one way to compute this eigenvalue, eigenvector pair is something called a power iteration method. It's implemented here, and we can see the results of this matrix. So this is implementing a double precision D general matrix. So DGE is a double generalized matrix. Sometimes in some other scripts you might see an FGE for float general matrix, but it is a matrix of dimensions 3 by 3, and the 4, 2, 3 are the first column. The 2, 5, 1, second column, and the 3, 1, 6 would be the third column. So we can see this in our actual code. So let's go to our eigen code. Let's jack in, which is Control-Alt-C, Control-Alt-J. I'm going to click our deps eden. So this injects our libraries that we need. I select our dev alias, which has included dependencies, and we're just going to run this script. So here is that DGE I wanted to show you. I'm going to run this full file with Control-Alt-C and Enter. So doing that, now, once it runs, I have access to all the functions, with this defn, this is defining a function, and all the variables. So this is a def for defining a variable. So I'm defining variable test matrix as this matrix. So we can see this matrix, again, it's a 3 by 3 with the first column of 4, 2, 3, 4, 2, 3, second column of 2, 5, 1, and so on. So if we look this power iteration way on the test matrix itself would give us that lambda phi. So this is our top explaining of variance of this matrix. This is the top lambda, and its corresponding phi, its corresponding eigenvector, is this 0.57, 0.44, and 0.69. So another way to compute the eigenvector, eigenvalue, eigenvector pair is this QR method. This is just a second way, and we see here actually this is computing our eigen values. I know it's a vector, but this 3 by 3 matrix A that we're passing has 3 corresponding lambdas, eigenvalues. That first one we saw from our power iteration method was that 9.14. But we're also given the additional second lambda that explains the second most variation in the data, and the third. So these are our lambdas, and this is actually going to be a capital lambda because it's a vector instead of just a value with our lowercase lambda. Next, let's look at this eigendecomposition, which does a lot of heavy lifting in terms of our PCA. It is this capital phi, which is a matrix of our eigenvectors. This capital lambda, which we just saw, this in fact is our capital lambda. It is a vector of our little lambda, i.e. the eigenvalues, and then the inverse of the eigenvector matrix. So this, we can decompose our A into this capital phi, capital lambda, capital phi inverse. So this is called eigendecomposition, and it's a big fancy function, but effectively what it does, it gives us our lambda, our capital lambda, which we saw from our QR method that's above at 9.14, 4.38, 1.47. It's the same values, but in this form, as well as our capital phi. So these are the eigenvectors. The columns are eigenvectors corresponding to the eigenvalues. So we saw this in our power iteration node, our power iteration method, the 9.14 with its 0.57, 0.44, 0.69, again, in our first power iteration method. So again, we got 0.914, 0.57, 0.44, 0.69. So the power iteration method provides us the pair, the eigenvalue, eigenvector pair of the most explained variance in our A matrix. So that's this. But this eigendecomposition gives us everything. So it gives us all the eigenvalues and their corresponding, as columns, their corresponding eigenvectors. So what we can do to test, what we want to do is validate that this A phi minus lambda phi is 0. It should be 0, but because of our precision, either double or float, we might not be 0, so I put it approximately. So here we just want to test as an eigenpair, so give us some kind of threshold, and then take that, we scale. This is effectively minus a v. Again, remember I said v, x, phi's are interchangeable, so this is our a phi minus lambda phi, should be 0, or again, less than our tolerance. So although here you'll notice I have a bunch of print lines, they don't print in this clay rendered workbook, but they do print in the REPL. So if we go down to the bottom, we have these functions, and again we can see our test matrix is at 4, 2, 3, 2, 5, 1, and we want to test is this an eigenpair, and it says true, true, true. So the first eigenvalue, that 9.14 that we keep seeing, and this corresponding first eigenvector, again this is 0 index, so this is first, the 0 comes first, and a 0 index, and the corresponding eigenvector is that difference, that a phi minus lambda phi. Yeah, it's pretty much 0. And all the corresponding eigenvalue, eigenvector pairings are true, true, true. So in our descriptive, we have the standardized function, we have the center function, and we have min-max and feature. So you can see what center does. For centering, if you look at a raw, centering effectively is looking at the mean, and then taking the mean away from each of these values. So the mean of 4, 2, 3 is 3, 4 minus 3 is 1, 2 minus 3 is minus 1, 3 minus 3 is 0, and the same throughout each of these. So we can see if we standardize it, do we get eigenpairs? True, true, true. Very good. If we center it, do we get the same? True, true, true. True, true, true. True, true, true. Great. So any kind of nice scalings that are common in scikit-learn or other data learning libraries that I implemented here are also giving us proper eigenpairs. Next, let's look at our PCA. So here we're talking about decomposing the eigendecomposition function from here. We decompose the covariance matrix. We do have center data that we just showed in that script, but I wanted to do a little bit more. I wanted both the matrix, the centered matrix, and the corresponding means. I wanted them both. So I just kind of re-implemented it, same with scale. I wanted the scale data itself and each of the corresponding standard deviations. So here is the PCA fit, and what we're doing is we're getting the components of this fit for the matrix that we pass. So the components are the eigenvectors, the variances, the explained variances are the eigenvalues, and so on. So here we want to transform, given that PCA model that we just built from PCA fit, if we give it a matrix, we want to transform it based on those eigenvectors. So here we transform our 1, 2, 3, 4, 5, 6 matrix. We fit it. The PCA fits that same one, and when we transform it, we'll get this kind of, to us, meaningless matrix. But the interesting part is we can inverse transform this matrix to get it back to our 1, 2, 3, 4, 5, 6 matrix itself. So down here, we'll see this is exactly what I just showed you above, that we're transforming the 1, 2, 3, 4, 5, 6 with the model of a PCA fit on that same matrix, and we get that kind of goofy matrix. But now I want to inverse transform. So this corresponds exactly to this matrix, that PCA fit, and when we run it together, we get back our 1, 2, 3, 4, 5, 6 matrix. Next, let's look at a basic PCA analysis in Python. I don't need to explain this code very much, because this is not the important part. But effectively, what we're doing is doing an analysis on the very common iris dataset and producing PCA analysis. So one is just a plot of the top two principal components, principal component 1, principal component 2. They have high levels of explaining all the variance in the data, and this image probably looks a little bit familiar if you've done some kind of clustering or unsupervised learning. Another nice plotting to do with PCA is called the SPY plot. So it shows the magnitude of push for each of these features. So if you have a higher sepal width, you get pushed in this direction of the principal components, versus a push of higher sepal lengths. The higher the value, the more the push along this axis of the PC1, PC2. And then we can have this explained variance. The next, now this is our implementation. We're reading in the data and giving it column names and kebab case keywords, because that's how Clojurians do it. I'm converting this data set into a matrix with this helper function, while also dropping the variety, the Sudsoda, the Virginica, those names. We don't want those. We just want to look at the X matrix. This is the Python implementation, and this is our function to implement it. So what we're doing is performing a PCA on a matrix X. We perform the PCA model fit with our model fit that we discussed here. We are both centering it and scaling it, and we're putting it on that matrix we feed it. And we transform the data itself with that PCA fit that we bind it here, and then associating. We're adding to that map of explained variances, components, the ratio, the means, the scale. I'm just adding that transform into this map. So now we have this transform matrix. Next, let's plot it. Well, okay, I guess before we plot it, we want to reconvert some matrix to a data frame that we can plot. So to do that, I have this helper called matrix to dataset, and so what I'm doing is performing that PCA on the matrix, grabbing that transformed map, so this guy, and then I'm taking this as a proper data frame, not a matrix, a data frame, and naming the columns properly. So in this function, actually, I arbitrarily label the first column x1, the next x2, x3, x4. So I'm remapping x1 into PC1. I'm remapping x2 into PC2, remapping x3 into PC3, and so on. Next, I take that data that we just made, and I pass it to this plot function. So this is a relatively new library in the Clojure data science stack, ggplot. It does a nice way. You'll notice this looks a lot like ggplots from R. In aesthetics, you would put your x equals PC1, your y equals PC2, and so on. I also attached back the variety so we can color it, and you'll notice it looks exactly the same as the Python, except we're mirrored over this y equals 0. This y equals 0 axis. So this point right here, that PC2 is going to be negative 2.3 on this implementation, but the x's are all exactly the same. So this tells us our implementation at least works, which is really great. And then the next, we want to make those arrows for that biplot. And we have the same exact biplot, again, just mirrored over the y equals 0 line. So you'll notice the magnitude, for example, the sepal width, your push in this PC1, PC2 dimension is the highest, and push down to the left. The sepal length will be, the higher it is, the more the push in this dimension with PC1, PC2, and so on for the other two features. And finally, we have the variance analysis, which we saw also in our Python PCA analysis. So here, I want to thank you for watching this presentation. I hope you enjoyed it and learned something too.